Thank you, Andre. And thank you for you and Patrick for the kind invitation. I'm really glad to have the opportunity to present to you this work, which is a joint work with Jean Auriol, who I think is online. Even, yeah. So this is the result of questions that we started asking, wondering about, I don't know, a couple of years ago, and which deals so with input-to-state stability and stability and control, of course, also of linear difference equations, or as I will try to illustrate it, equivalently, the stability and control of first-order linear partial differential, hyperbolic partial differential equations. So, namely, we're interested in hyperbolic PDEs, so which I'm gonna detail in a few minutes. So here are just a few examples of physical systems that I had the opportunity to work on over the years, and which could be modeled in certain circumstances, let's say, by hyperbolic PDEs. So let me start by maybe the one that most of you know, which are heat exchangers. And here in the picture on the top right of the slide, I picture a counterconvective heat exchanger, where you aim at controlling the distributed temperature along the exchanger and thus maximizing, for instance, the amount of exchange power between the cold and the hot channels by acting on the flows of the two channels and also on the temperature at both boundaries. So you have distributed exchanges, which comes from convective exchanges along the exchanger, along the channels. And then the two flows are also flowing, so you have a transport equation which models the evolution, the dynamics of each of the temperature. And interestingly, in this problem, you don't have any information along the channels. You only have actuations and measurements at the boundaries. So this is one example of a system which is modeled by linear first-order hyperbolic PDEs, which are actuated and measured only at the boundaries. The same happens in other contexts where you also have transportation material and or vibration. Transportation of materials, that happens, for instance, also in catalyst, which is modeled on the bottom left of the slide. This is here an example of a three-way catalyst, which is a catalyst used in gasoline engines in order to convert pollutants resulting from the combustion of inside the chamber. So you have different pollutant emission, which you want to convert, so either oxidize or reduce. And this you do, this is why these catalysts are called three-way catalysts, because it proceeds to two reductions and one oxidation of the pollutant emissions. And the thermal behavior of this catalyst is crucial when you aim at controlling the efficiency of this conversion. And interestingly, well, this model involves also thermal exchanging, like in the heat exchanger, which are captured by first-order hyperbolic equations again, with a small diffusion factor as well that could be ignored at first order. Another example of transport occur in wind farm. So this is a PhD thesis that I have supervised lately, in which we were focusing and aiming at obtaining simple model of the wake. So the wake being this picture that is seen here in a farm, wind farm in Denmark, which is quite well known, the Ornrev Free farm. So you have a loss of a deflection of wind due to simply, well, the wind turbine capturing a part of the kinetic energy of the wind. And so the kinetic energy, the wind speed just after a wind turbine is a bit decreased. And this creates these wakes that are visible on this picture. And interestingly, so the simple enough model, which is a control-oriented one, is a transport equation, a cascade of different transport equations that are then superposed to account for the interaction between the different turbines. So all of these models then, all of these systems, sorry, can be approximated as this model by first order hyperbolic PDEs. So in terms of equation, here is a system that we're going to be interested in during this presentation. All of you already know it. So we consider U and V two vectors, distributed variables. So U are taking values in Rm, Uxt, Vxt taking values in Rp, for instance. U as a quantity pictured in green on the picture on the bottom, which travels then from the left to the right, from x equals 0 to x equals 1. Okay. And each of them, U1, U2, U3, etc., have a different positive velocity, which is denoted here as lambda 1. We assume without loss of generality that these lambda are ordered. So lambda 1 is the smallest velocity, lambda n is the largest. They interact with V, which through these terms sigma plus plus and sigma plus minus. So sorry, sigma plus plus is the interaction of U with itself and sigma plus minus with V. And V is transported in the converse direction from x equals 1 to x equals 0 with, again, different velocity, which are supposed to be ordered, but now negative 1. So from mu1 up to mu p. Okay. Then you have also boundary condition linking what's going on at 0. So U of 0 is supposed to be related to V of 0, what is flowing out of the system through the matrix P0. V1 is related to what's flowing out of the U subsystem through the matrix R1. And we assume that, for instance, we control only what's going on at V equal 1 through the input capital U of t. Okay, so this type of equation, it indeed models, for instance, the heat exchanger, where U and V would be simply scalar variable, accounting for the transfer the temperature along the channels. Sigma plus and sigma plus minus here would be then H or minus H divided by the surface, being the H being the convection parameter. Okay, so all of this distributed term sigma here in this exchanger case would be could be considered as constant parameters with a different sign and just accounting for the convective exchange. Q0 and R1 in this case of the heat exchanger would actually be equal to 0 because you would control well, apparently if you're in open loop, at least you would simply control this thing by exogenous signals without necessarily having a coupling with between the system. Okay, so this is the type of system and models that we are interested in, and a lot of works have been dedicated to control, estimation, identification, observation, etc. of this type of system in the last decade, with a lot of experts that some of them being here today. So I'm not going to go into this thing. What I would like to start with, so an observation that I would like to underline first is that looking at the system is equivalent to looking at another type of system, which are linear difference equations, and that I'm going to present now and are going to be the focus of this talk. So, namely, as I was saying, we can represent this type of hyperbolic PDEs by a linear difference equation. So I'm just gonna, and this is through the characteristic lines, and I'm gonna illustrate this here with a simple example where I have n equal 1, so only a scalar variable for U, and two lines for V, V1 and V2. So if now we look at what's going on for V at x equal 1, so we have V1 of t through the boundary condition of V equals to R1 U1 t plus U of t. And U at 1 can be related to U at 0, but delayed, if you integrate through the characteristic line of U. So you get this relation R1 times U of 0, but delayed by 1 over lambda. Okay. Now, U at 0, you can use again the boundary condition of U at 0 and replace it in terms of V1 and V2. Okay. And this V1 and V2 at 0, again through the characteristic line, you can relate them to V1 and V2 at x equal 1, but delayed again by their respective transport time, which are 1 over mu1 and 1 over mu2. So in the end, we get what is called a difference equation, meaning a relation between V1 at time t and V1 at path values of at path values of time. So this is an equation which does not involve a differential operator, right? This is not a differential equation. This is a difference equation. And so this is a specific type of time delay system because you do have this pointwise term. And so looking at trying to stabilize V1 at t then results into the stabilization of U and V1, V2 because you can move from one to another. So this is the results that Jean Auriol and Florent Di Meglio published in 2019 because here, for the sake of illustration, I just put an example where you don't have source term, where a situation where it's very simple, but you can actually generalize this thing in the general case that I presented before, and proves that there exists a function Gij, which do depend only on the source term, I believe, no, as well on the also on the sigma, but also on the transport speed. And prove that the stability property of the system of linear first-order hyperbolic equations are equivalent to the one of the difference system, linear difference system, which is given here in terms of Z, which involves pointwise delays as previously. So you have this VL of delayed by 1 over lambda k plus 1 over mu L. Okay, so those are pointwise delay terms, but also distributed ones. So this integral between 0 and tau mu plus n of VL. So this is a bit more complex than the equation that I had before because of the distributed term, but again, this is a different equation in the sense that it's an equation relating V at time t with path value of itself and of all the other coordinates without having a differential operator. And so I was saying that the stability properties of this difference equation is equivalent to the one of the original systems of hyperbolic PDEs in the sense given in the equation in red, which tells that you can upper and lower bound the L2 norm in the space term sense. So this is the L2 spatial norm of U and V by an L2 norm of V. L2 now having to be understood has a time domain norm. So according to this formula, then, if we, as we have this equivalence, so this upper and lower bound, if you stabilize Z, you stabilize in terms U and V, and the same for U and V. If you stabilize it, you stabilize V in VT in terms. And moreover, convergence, you also have exponential stabilization and asymptotic stabilization, if you wish to translate the properties. So this means then that equivalently, if you want to tackle the stabilization and control of the linear difference equation of the sort of the system of hyperbolic PDEs, you can look at the difference equation and maybe try to establish something for this difference equation. And then in terms you're going to obtain similar properties for the original system. Also, interestingly, you can prove that there is an explicit mapping linking Z and U and V. Okay. Oh, by the way, I forgot to mention at the beginning that if you have any question, of course, feel free to interrupt me anytime. The more interactive this talk is, the better I think it will be. So this gives you now the outline of my talk. I'm going to just present a bit more some properties on linear difference equation, just for your curiosity and for the sake of completeness, give you a few properties. There are not that much things and works that have investigated this question, so this will be very brief. Then move to the main question that we tackled with Jean, which was trying to establish a converse ISS Lyapunov theorem for these linear difference equations. And if I have enough time, I'm going to illustrate to you why we were interested in this question with another problem that we were interested in, which is the boundary control of networks of this type of system of hyperbolic PDEs that I presented. So in this talk, then we're going to focus on this type of systems, so which are delay difference equations. Then X is a vector in Rm, and we're going to be interested in X t, which is the path of X over time horizon minus tau m0. Okay. X satisfy this dynamics in which you have m different delays, which are supposed without loss of generality to be ordered and constant as well. And you also have then this distributed delay with a kernel n, which is supposed to be a piecewise continuous function. And then we're also going to look sometime at the inhomogeneous problem, where the exogenous function signal f is acting on the system. A few remarks. The first one is that picking the distributed delay as equal to the maximum pointwise delay is not restrictive, because you can still go to formulate things into this framework, either by picking n equal to 0 on a certain time domain, or by introducing virtual matrices A, which are equal to 0. Also, this is very, very short remark. It's just that if you have delays to k, two delays to k and to l, let's say, which are commensurate, so which have a common factor, you can still extend the state to go back into a setup where all the delays are supposed to be rationally independent. So this is important for later use. So you can, without too much loss of generality, assume that the delays are rationally independent. This is not a big restriction. Okay, so the motivation for studying this type of system basically comes from two problems. The first one is that it's usually necessary to first look at this equation when you look at more general class of time delay systems, which are natural time delay systems. So system of this form. So in which you have delays not only then on the right-hand side of the equation, but also on the differential operator. And you can prove that actually a necessary condition for the exponential stability of the natural equation is that the operator d is itself exponentially stable. So you may want first to investigate the exponential stability of this operator d before going into looking at the natural time delay system itself. So this is one motivation. And another one, of course, is, so this is the one of the only examples that I had in mind that I know, which explain why people were looking at this thing, but they were considering then linear delay difference equation as zero order, let's say, natural time delay systems, so a very specific thing, and so less studies were dedicated then to this type of system. Another one is the one that I just mentioned, which is the equivalence with hyperbolic PDEs, that very few works have investigated this question up to my knowledge. So in terms of existence of solutions, the only result I'm aware of is the one given by Ale and Delphine, where if they give the existence of piecewise continuous solution, if the initial condition is initialized in the set of piecewise continuous solution equipped with the infinity norm. Later, in other work with Carvalho, they say that this is equivalent and we can prove things in a different functional space, such as LP spaces, but this is just remarks which are very briefly given up to my knowledge. So the only formal proof that I know of is the one for piecewise continuous functions. Now, a few remarks on how we can equivalently write the stability of this type of equations. So again, in the book of Ayle and Virginia now, you have the following result, which says that the operator D corresponding to our equation is stable. So this is the operator is called stable if the zero solution of the equation is asymptotically stable. So this is a bit misleading, but this is the vocabulary that you use, so I'm going to stick to it. So it is stable if and only if, when you look at the spectral operator delta given here, which is nothing more than the Laplace transform of the operator, if the supremum of the real part of the spectrum is strictly negative. Or again, that you can find a line located at minus delta, such that the real part of all the lambda of all the spectrum is on the left of minus delta. Or again, that you can find positive constant C and alpha, such that the norm of x at time t is upper bounded by this sum between psi exponential minus alpha t and the supremum of f. So this means that according to this result, the asymptotic stability of the zero solution is equivalent to the input-to-state stability of the system. Okay, so we know now that if the linear delay difference equation that we are looking at is stable, then we have for free, in addition, the input-to-state stability of the system. And well, this is not a really surprising property, right? Because we're looking at two linear systems, so it comes naturally, well, intuitively, everyone would agree that the addition to a finite signal would lead to a property of input-to-state stability. But this is a result that is, you know. Unfortunately, the thing is that the concept of stability is not sufficient to guarantee any continuity and any robustness with respect to uncertainties and the delays. And you have examples which are given that for which you have stability for one value of the delay, and as long as you disturb a bit, even a bit infinitesimally, the delays, the stability is lost. So to be able to guarantee such type of continuity with respect to the delays, which is a property that is going to be needed in any controller that we're going to design, we need a stronger result, which Ayle and Virginia called strong stability. So this result is only holds for a case where the operator D does not have distributed delays. And for this type of operators in which you don't have distributed delays and the delays are supposed to be rationally independent, so here comes my previous assumption that this is not something which is very restrictive. Then you can prove that the operator is stable if and only if it is stable locally in the delay. So you have equivalence between stability and some robustness in terms of with respect to the delay. And surprisingly, this is also equivalent to a global stability in the delay. So this means that requiring to have a small margin of error of robustness is equivalent to actually having stability, whatever value of the delay you're looking at. So you have this for free in some sense, which is very interesting. And finally, all of this is equivalent to this spectral condition that the supremum of the spectrum of the sum of ak exponential I theta k is smaller than 1, strictly. So you have a numerical criterion that you can check, and people are investigating the questions of having tools which are numerically efficient to check the strong stability. Okay, so all of this being said, this tells you a bit where we stand. So we know that we have, when we look at the linear difference equation, that strong stability is a concept which is important. We know that it's equivalent to, at least when we are with rational independent delay, equivalent to input-to-state stability, that's all. So our question here that we had was to say, can we establish input-to-state stability? Sorry. So can we establish a necessary and sufficient condition for input-to-state stability in terms of a Lyapunov functional? So can we establish a converse Lyapunov theorem for this type of system? We were led to this question because at some point, this is an example that I'm going to show later if I have time, we needed to get such a Lyapunov function for a cascade of system. We wanted to have one, and so naturally we came up with this problem. So I don't need to recall the definition of ISS for the seminar, of course, but here it is in the case of linear dynamics. So I'm taking this exponential terms instead of KL function, but you recognize all of you recognize the definition, so I'm not going to go say more about this. Another just brief remark is that, so this is what I mentioned briefly at the beginning. In one of the paper of Ale and Virgin Linnell and Cavallo, so it's mentioned that L infinity ISS, that is a concept that was presented previously, is actually equivalent to L2 ISS. So, which is the concept that I put in this slide. So, the functional space are supposed to be well, even if the functional space are not the same, the two concepts of ISS are equivalent according to this result. So we're going to look here at the L2 norm because this is the norm which makes more sense for PDEs, but we could also establish similar thing for L infinity. Okay, so now here are some relating results regarding input-to-state stability for this type of system. So you had a few, a large variety of results for PDEs, which are summarized very well. So in the SCAM review paper of Andrei and Christophe Prieur in 2020, which proves that the theory of input-to-state stability, its relation with corrective function is really well established when you have bounded operators and also unmissable input operators, but this is not the problem at stake here, right? We're looking at boundary operators. And so in the remaining cases, you have some results that exist, but fewer. The most important one may be the one by Jean-Michel Coron regarding strict Lyapunov functional. So under certain dissipative boundary condition, he establishes that the pure diagonal functional V that I put here is an ISS. No, sorry, is not an ISS. It considers f equals 0. Sorry. So this is sorry, a Lyapunov functional of interest for proving the exponential stability of the system. But this is so under this dissipative boundary condition, which is a bit conservative. A few other results. So Anil Tanwani, Christophe Prieur, and Sophie Tarboyash also investigated this question for system of balance law under the dissipative boundary conditions, but again, those are sufficient conditions. And Yason Karakidis and Miroslav Pirsic also had a large variety of results on the ISS for PDEs, but the only cover, as far as I know, unidirectional hyperbolic PDEs in this book, which is not the case that we're interested in. Also, so you have results now. So as we don't have the result that we're looking at for hyperbolic PDEs, let's look at what's going on for different equations. So I'm going to skip the first one because this is the one that I'm going to detail later. But the only two results that we found are one from Domenico Pepe in 2014, where it characterizes the Lyapunov, the input-to-state stability with a Lyapunov function, but with a difference operator. which makes sense because we were looking at difference equation, right? But here, as we're interested in going back to the hyperbolic PDEs, having a relation, we would be more interested in having a differential operator. So this is not exactly the result that we aim at obtaining. Again, Yassen-Karatoris and Miroslav-Pirsich established a Lyapunov characterization of a nonlinear delay differential equation, so which is more general than the context that we're looking at here, but they established only sufficient condition, which is already, well, a very satisfactory result, but we would like here to have something which is sufficient and necessary. So we can directly use this methodology. On the other end, recently, so Sabine Mondier and Michael Di Loreto with their student Manuel Rocha-Campos looked at necessary stability conditions for this type of equation with the Lyapunov functions. So we were inspired by this result because we thought that we could modify it to establish necessary and sufficient stability condition. And this is what I'm gonna present to you now. So I'm gonna start just by giving you what they did and then explain to you a bit how we changed it. So the result is built on very classical method and tools for delay systems, but usually differential time delay system, which basically is giving the Cauchy formula. So what they call a Cauchy formula is the solution to the linear equation. So they establish what would be this formula for the dynamics of state, and then build on this formula to propose a Lyapunov functional by integrating the solution backward, basically. And this is the classical methodology that we use in converse Lyapunov Theorem, of course. So here, for our dynamics, they prove that by introducing this fundamental matrix K here, which satisfies, oh, sorry, I forgot to mention that in the rest of the slide, I'm going to focus on the case where we don't have distributed delay terms. This is what they do in this paper. So they do that in this paper. We were able to have a more general result with distributed delay, but I'm not going to present them for the sake of simplicity and go back to this later. So in this slide, they consider only pointwise delays. They introduce this fundamental matrix K, which satisfies the same dynamics. So that's in the reverse order. K is on the left. And K is constant initially. So you have a constant initial condition, and then this delay differential equation, K being a matrix here. So this K here will have will be uniquely defined. And in terms of this K, you can define X has the sum of the Dini derivative of this distributed delay term involving K over there. And so this is proven to be the unique solution to the linear delay difference equation at state. Let me mention that K here is very specific because as it is initially constant, it will be piecewise constant. Because so you have something which is constant initially, then at time 0, you have a new K, you switch, but this is again a constant, right? Up until, so the right-hand side is constant, up until you reach the first delay, which is tau 1, where the value K of T minus tau 1 then will switch, so you jump. And again, then at the next delay, which is, I don't know, 2 tau 1, for instance, or tau 2, whatever. So you have a piecewise constant matrix with discontinuity points being the set capital T, which is the set of linear combination, so integer linear combination of the delay. Okay, then what do they do? So they start, they look for a quadratic functional, which is such that when you take the Dini derivative of this 0, you recover a quadratic term of the state X at time T. So they start from that. Then they integrate the this dynamics between a time t0 and a time t, which gives us that v0 at x of capital T minus v0 at phi is equal to this integral. If the delayed differential equation is supposed to be exponentially stable, then you can take capital T tends to plus infinity, v0 tends to 0, so you recover v0 of phi, so the expression of v0. Now, we use the Cauchy formula. We replace x of s inside the integral by the Cauchy formula that was obtained before in terms of the fundamental matrix. You apply Fubini, so you switch the different integrals, and you finally get this form of quadratic function in terms of matrix written in blue here, which is a bit complex, which involves the fundamental matrix, but still, this is only just a quadratic functional. Okay, so you need then to look a bit more at this term that was written in blue, and you can actually prove that this is the second derivative of this matrix, which is called the Lyapunov matrix, which is, again, something very standard for time-delay system and complex type functionals. So this U defined here can be proven to be almost everywhere differentiable, and that its derivative is expressed here in terms of the fundamental matrix again, where delta K here is the jumps of the fundamental matrix K. And you can so prove that this matrix blue, this matrix which was written in blue before here is the Lyapunov function, is the double derivative of the U. I'm going to come back to this later. Another thing that they do is that, so they have this matrix, okay, it satisfies this derivative of the derivative along the trajectory being equal to minus x of t w x of t, but this is not enough to prove anything because a priori this function could be, for instance, negative. You don't have any idea of what are the signs. And to, well, be able to relate this matrix to the L2 norm, they had then a term to a quadratic term directly to it and prove that you can find an alpha such that D1 is lower bounded by alpha times the L2 norm of phi. So the proof is very basic. They just take the time derivative of d tilde, has d tilde being the difference between V1 and alpha, the L2 norm of phi. Due to the fact that d plus of v0 xt is equal to minus xt w xt, you obtain this equation. And so the first term is negative, and then you only have to satisfy the second one to be negative. And so to guarantee this, you just pick alpha as lower than the minimum eigenvalue of w being positive. This number is positive. And thus you can guarantee then that for any alpha lower than this, the result of the sum between v0 and the L2 norm, weighted L2 norm, is larger than the L2 norm of phi. So this gives us then, so they gave us then a functional v1, which is a Lyapunov function, and this is a necessary condition then to have the exponential stability of the original delay difference equation. So the question we had was, okay, so that's nice. We have a functional which is working when we're looking at the homogeneous equation. What's going on if now we had this additive signal f? And we wish to study if the Lyapunov functional that we had before can still be used in this context, and if we can establish input-to-state stability. So what we did, which was a bit complex in terms of computations, but quite straightforward in terms of steps, was to take V0 and then now look at what is its unique derivative along this new inhomogeneous equation. So I'm gonna just skip this thing and come back later, but here is a result that we obtained. We had that d plus v0 so when you evaluate this d plus v0, you get now that you have minus x transpose wx, so the quadratic term that you had before, and additive term depending on f of t, of course. The two first one in black here are well, nice guys, let's say, because they are only coupled terms or quadratic terms of ft. So this is good in terms of input to state stability. You can bound them then by quadratic terms of f. There is no problem. But you have a bad guy, which is written in red here, where you have cross term between f of t, but also delayed terms, pointwise terms of x, which so are certain numbers and come from discontinuities of your prime, basically. So the proof of that is a bit long, as I mentioned, and tricky, and it uses a lot of properties that algebraic properties of this Lyapunov matrix U, which are called the symmetric property, dynamic properties, and generalized algebraic properties. But roughly speaking, we obtained this thing. So the good thing is that the sum of delta U prime here of the time of discontinuities of U prime is actually a quantity which is finite. This is a result that we prove. We prove that the matrix U prime is, so as K is piecewise constant, U prime, which, do I have it? Yes, I have it here. U prime involves the fundamental matrix K, which is piecewise constant. So U prime in terms is piecewise constant. And then it sets of discontinuities. You can prove that it is countable because it's the time such that tk minus t is equal to another tj, for instance. So you basically have an n squared, which is countable. So this quantity is finite. So here, to bound the red term over there, you can put the sum of the delta U prime tau c outside of the sum, and you can use Young's inequality. So those are the issues that were remaining. We had to tackle this red term. So this we did, has the sum is finite by adding integral terms of L2 norm with a certain sequence of delays and suitable decay to bound all of these pointwise delay terms of x. We also had to obtain the equivalence with the L2 norm because for the moment we're working with the zeros. This we obtained by adding an integral term as they did in Rocha Campos Italy. And finally, to get a strict Lyapunov function, which they did not have, but for this you simply had forgetting factors of the form exponential rho nu. This is the classical standard trick for tabular system and hyperbolic PDEs. And this leads us to this following Lyapunov functional, which is, well, a bit long with various terms, but that has the merits of being roughly explicit and quadratic in terms of the phi. So we were then able to establish this theorem, which tells us that the input-to-state stability, L2 input-state stability of this inhomogeneous equation is equivalent to the existence of the quadratic function v1, which is such that the linear derivative of v1 is upper bounded by minus rho v1, so certain for rho a certain positive number, plus sigma f squared. So the classical Lyapunov inequality that you have for input to state stability. And second, that you have the equivalence of v1 with the L2 norm of the L2 norm. So upper and lower bound in terms of the L2 norm. So in the slide that I presented, I only prove that one involves two, right? We constructed constructively, so this quadratic function. But of course, proving that two implies one is very straightforward. You just use Barbara's lemma on V1 and everything follows very straightforwardly. So this is the simplest. This is a simple. So the other implication is the simplest one, and so I'm skipping it. Okay, and interestingly, we also have so a similar result now, but for systems of conservation laws. So if we go back to the PDEs, if we look at a PDE which has no source term, then we have equivalence between exponential L2 ISS of this system of conservation law and the existence of a product extension which satisfies the exact same properties. The reason why we had to look only at conservation laws to remove the coupling term is due to the fact that we're not able to formally write the functional that we obtain in terms of the PDEs, so as the state of the linear difference equation back to the PDEs. But I'm gonna explain this a bit more now. The main result also is that here we were looking at cases where we don't have distributed delays, and this case corresponds to the case where you don't have source terms. Okay, so the points that remains to be tackled are so as I was just saying, the extension of this result for general classes of first order hyperbolic PDEs, not only balance laws, not only conservation laws as the one I was presenting before, so without source term, which equivalently then can be formulated as a problem of having this result for linear difference equation with distributed delay. So we believe that we have this result with Jean that we obtained with students that did an internship with us. But we only have this result now for this difference equation, and we are stuck in trying to write this problems in terms of the original PDEs for the moment. So there is also still some questions to be answered on that front. Another problem is also that we use different norms, as you saw. So we have to consider that that the initial condition is piecewise continuous while we look at the L2 norm. So we would like, if possible, to get rid of this assumption, but that may be a bit complicated. And finally, to try to apply all of this for the robustness study in the context of PDEs. So yeah, I don't have that much time, but just wanted very briefly to explain to you this last point on why we were interested in this problem. So this is because we considered this type of problem where we have a network of hyperbolic systems of hyperbolic PDEs. So this, for instance, you can have when you have I don't know, networks of electric lines, for instance. So you do have parts of the networks where the channels are interacting with each other, so leading to this system of conservation laws. And then you have just points of the networks where they interact, but it's really just at the boundary. So this will lead here to the control at one boundary, here at x equal 1, of the two subsystems. And you aim at controlling all of these only acting at the boundary. Okay. So I'm going to call this system, which is close to the boundary, proximal, and the one after that distal. So the approach that we applied with Jean was to make first a transformation on the proximal subsystem that I'm going to skip. But yeah, basically, we were able to work to reformulate the system in such a way that if we're able to control what's going on the beta dynamics, so the bottom one, the transform one corresponding to VP, to the proximal V subsystem. Then, so we act on the distal subsystem in a delay manner, so through the blue lines over there. And then, if we're able to stabilize what's going on in the distal subsystem, the stabilization of the proximal will follow. So we're basically left with this type of problem where we have a system of hyperbolic PDEs controlled at the boundary but delayed. So we worked on this to so to predict, build a prediction to be able to control this tools system. And basically we were left with this problem of, so we had a nominal controller that was working, that was able to stabilize the hyperbolic, the entire network of hyperbolic PDEs. But this problem opens new questions, because we know that prediction-based controllers are sensitive to input delays, to uncertainties varying on the input delays. So we wanted to evaluate the robustness of this controller. This explains why we were interested in having Lyapunov tools to analyze this robustness, as was done, for instance, by Miroslav Kirstich, Nikos Liberis, Bresch-Pietri. They used the delay Lyapunov functions to analyze these delays, and we wanted to have the same tools. So this is one example of context in which having an ISS converse Lyapunov theorem would be extremely useful. Okay, so I'm just gonna finish with a few perspectives. So as I was saying, the first question that we would like to be able to tackle would be to express this ISS Lyapunov functional that we were able to obtain for linear difference equation with both pointwise and distributed delays in terms of the original variable of the PDE. This would be a very interesting contribution, in my opinion. Apply all of this to be able to analyze the robustness to delays. For instance, when we are looking at cases where we're controlling the system through a prediction, as in an example I was showing. And so I went a bit quickly on this last part, but regarding to the prediction, we have a lot of questions that come into mind now that we have a first design. Namely, we would like to extend it to multiple input delays, and also, and more importantly, study the robustness of all of this to delays which are uncertain, etc. And this will be done through the use of this ISS Lyapunov functional. So this is all. This concludes my talk. And if you have questions, I would be happy to answer them.